I would like to thank first Rui. That's Enrique. Yeah, exactly. I would like to thank Rui and the scientific committee for the invitation, and Enrique Wusting for organizing everything here so nicely. This is some project that I started some years ago when I started reading the paper of Enrique, Gil, and Marco about reduction of Dirac structures, and I was puzzled by the following fact, which was that on my previous work I was working on certain gerbs on orbifolds, and I wanted somehow to bring them in a specific way on orbifolds that were not so much ad hoc, and I thought that by reading or learning about this current algebras, I could get a hold on a nicer or better description for these gerbs on orbifolds that would lead me to somehow understand in a better way what was its relation with certain Gromov-Witten invariants. Well, unfortunately, this didn't happen because I couldn't really see how could I put torsion information on the gerbs coming from current algebra. But on the way, I somehow got interested in how can one find or define an action of a group or lift an action of a group into a exact current algebra. So there are several ways to try to do this, and in the paper already by Enrique, Marco, and Gil, they already have a description of how to do it, but I wanted some description in which I could somehow make an action of any Lie group into the current algebra and not somehow only compact. And I will tell you, well, so what's my setup here? I'm just putting the definition of the exact current algebra. I'm not putting the 5 axioms because you can deduce them from this information. And what I want to solve or to answer is if I have a group, an action of a group into the manifold M, how do I lift it to the exact current algebra? In what sense can I lift it, and how could I do it? So this talk is very related to the talk of Ezra's 2 hours ago or 3 hours ago, and perhaps the overlap is quite big, because I think the idea is basically the same. So, of course, if I have a acting on a manifold, I have a map to the diffeomorphisms of M, and if I can find or understand the automorphisms of this current algebra that I'm denoting this way, and there is a nice here map, if I could in certain way find the lift, then I'm done, no? This would be the action. But I don't know what is this object. I don't know what is this, and it has to be some three group, but I don't know what it is. So what is going to be my approach? My approach is very pedestrian. So what I'm going to do is I'm going to approximate to the answer by looking at what happens infinitesimally, by figuring out what can I do with the group by hand, and then somehow in a somehow ad hoc way to give you the answer. The answer is, suppose, the expected one. So what can one say about the symmetries of this object? So one can start thinking or studying what are the derivations, somehow the symmetries, the infinitesimal symmetries of the current algebra, and this was studied. Well, if I'm quoting wrongly, then I excuse myself, and you could tell me what are the appropriate quotes. But I think the place where it was best written was by Marco, Gil, and Enrique, which is basically you have the vector fields which act in the appropriate way, and you can have the B field transformations, and these two things you can put them in a very nice Lie algebra, and the action is just given by the one on the bottom. So that's the bracket in the middle is the Lie algebra that they form, and the action is given on the bottom. But in some sense, when one writes the complex itself, that this thing, so one has the vector fields and the two forms, and I'm putting this H here, meaning that they satisfy the equation. can go to the vector fields, and here the kernel is closed formed. Well, in some sense, to me, when I saw this was striking to me, because what I would like to put here, as somehow Marcus talks, I would like to put here the 1 forms and the 0 forms, because I don't like to see the closed 2 forms by themselves. So the basic idea then underlying this whole thing is that the current algebra is a 2 object in the category of whatever, and of course if I want to find the symmetries, it will be a 3 something in the appropriate category. So this would be here the 0 symmetries, and there will be some homotopical or higher symmetries coming from the 1 forms and the 0 forms. So how to make this concrete, or how to make this understood? Well, this was already done by Dimitri. It's in his paper 2002, I believe. And he basically has the infinitesimal symmetries of current algebra embedded in his paper, but this, one has to extract them, and I'm just going to extract them in a simple way. So Dimitri told us how to, in some sense, understand or get kind of the moduli space of this exact, or in general, current algebra. Somehow he's always fixing the inner product, but it's okay, we're fixing it. And the way he did it is by finding a very nice symplectic and manifold on which the Maurer-Cartan elements would, for each one of them, you would get an exact current algebra structure. So, but if one knows that, then automatically one can see what are the symmetries of one of these Maurer-Cartan elements. It's just the complex behind it with the appropriate differential and the appropriate bracket. So if I think of a current algebra as one of these thetas, then the symmetries of it is just whatever is behind. I just put the differential to be the bracket with the explicit theta that I took, and I also have the Poisson bracket. So this is a DGLA, and this would be the infinitesimal symmetries of my current algebra. Now, if I just this is the description on top that Dimitri inserted, and in his paper is already somehow the nice description. If you put it in the exact case, that's what you get. So you get this complex of 3 elements on which you have the 0 derivations on the right-hand side, and there are these other higher derivations. Now, the differential is the first differential is just the RAM differential, and the second differential, perhaps you don't see it, is basically this vector field is in here. I'm just going to write the equation, so it's alpha, and the differential leaves x. Here is acting as contraction, he's acting as lead derivative, and send this to this operator that we already know somehow it exists. Well, so then this is the DGLA. I just wrote all the brackets for this differential graded Lie algebra of symmetries of my exact current algebra. Now, so if I already know what are the infinitesimal symmetries, then I could start playing around with the infinitesimal type of actions, and then I'll tell you how to try to make it global in some way. So what I'm going to call this with these German letters, or it's going to be the symmetries of the current algebra, and it's going to be this DGLA of size 2 or 3. So, but instead of keeping myself in the world of current algebras, I'm going to switch to another world on which the same DGLA appears, and this is the world of Rn bundles over the manifold in the category of DG manifolds that was developed by Chevera. Why? Because it gives me the same DGLA. It's basically because it's the same model line in some sense. It's easy to think in the other one. So I just forget that I have current algebroids, and I go to a specific construction of a DG manifold that was done by Chevera. So what do? I take the tangent space shifted by 1, and then I just put a vector space of degree, dimension 1, degree n, and I just want to define a specific homology vector field there that lifts the differential. So we should think of this as Chevera does it as a principal bundle, or as a bundle P, and then I have here the tangent 1, the manifold itself, and I want to lift this homology vector field to someone in here. that's somehow like a connection. And this is very simple to do it because in this case it's just given by an n+1 form, as Vedada constructed it. And if I want it to be a homology vector field, it's just given by a closed n+1 form. So as we can see, well, this Q is a derivation of degree 1, or a vector field of degree 1, or a derivation of the algebra, or a vector field. And again, I can play the same game, satisfies the Maurer-Cartan equation, and I want to get the symmetries of itself. So I just go and take all the vectors of degree less than 0, and I define a DGLA. So what is this? Then basically the same thing as before, but now I'm allowing it to go to any dimension. So it's a simple calculation. We just go and take a look at the vector fields, and I get the complex that is in the middle. So this is again a DGLA, and the brackets are the same brackets that I put before. And then we know, well, it's a simple fact. It's just in the case that the form is a 3-dimensional form, then the symmetries of the Courant algebra is the same as the symmetries of this homology or this homology vector field. Now, why this description is easier, you'll see, because then we can think about principal bundles in some sense, or vector bundles. So this description I learned from Dimitri, which he learned from Sobre. So the moral of the story, what I'm going to play around with is that in order to lift an action of the manifold to the Courant algebra, well, it's the same as to lift the action of the group on the manifold. It's the same as I have an action here, is the same as to lift it there. And with this description of the problem, then the answer comes by itself. Then we can see that somehow it has to be the equivalent cohomology already there. Because if this is classified by an n+1 form, or you could think of this as the KZN, and if I want to lift the action of the group, then it will become precisely what is the equivalent cohomology. But somehow this already told me what the answer was, but somehow I had to build it in differentially. So then this is what I'm going to try. But before going there, I just want to see some nice things that this DGLA of symmetries of the n+1 form gives us, because it's a very nice complex, and its derived algebra is quite interesting. So what I do is I take the derived algebra associated to the symmetries of the n form, which in this case gives us this complex that I have there. So it's basically I truncate. So the before was like this. So you have this is kind of the symmetries. So I truncate the complex here, and I just get the whatever is left with the derived bracket. So it was already shown by Yvette that this produces a Leibniz algebra, and in this case is a differential graded Leibniz algebra. But there are higher brackets, of course, of this thing. The higher brackets, I don't really can say much about them because I don't know exactly what they mean. But fortunately, recently has been shown by Uccino that these higher brackets also have some coherency conditions, and they become something that is called a strongly homotopic Leibniz algebra. But let's still concentrate only, say, with the DG Leibniz algebra and this complex, which is the derived gadget. That is, as you can see, if you put the n equals to 2, well, what we recover basically is the exact Courant algebroid, except that the inner product is never there explicitly. There is the other inner product times 2, but we recover all the brackets. So, yeah, in the case that I just said that the n equals, so that the form is a 3 degree 3, so we just recover the Courant Dorfman bracket and the 3 bracket, precisely all the information. Now, I just wrote here what is simple calculation, what would be the 3 bracket. To me, it doesn't say much. Perhaps to some of you it says something. But what is interesting is that I could cook up a sub-algebra of this one that that this has been called, or we could call that the one of Hamiltonian symmetries. So why Hamiltonian symmetries is basically because I want this equation here on the side to be equal to 0. And if I just take the subcomplex of this one, which is given on degree 0, and only on degree 0, the rest I keep it as it is, and on degree 0 I just take the vector fields and the forms on which they satisfy this sort of generic Hamiltonian equation, then this differential, this algebra, this Leibniz algebra, should behave or should be like the Hamiltonian algebra associated to the n form. So far I haven't said anything about being symplectic or enplectic, but somehow those should be the symmetries. And if I don't say it is enplectic, it's because I'm keeping always the vector fields together with the forms, so that I don't forget how is this equation being true. But this has been studied already by Baez, Hoffnung, and Chris Rogers, who is here, and has been studied specifically for the case on which n equals 2. So these are one forms. Yeah. In this case, one gets, specifically by simply calculation, one gets this very nice bracket. And in the work of Chris, that he put this here in the archives, he gives a different description of what could be the Hamiltonian, or say the Hamiltonian algebra, which is basically is taking the same complex, which I just said here, Ham 0, and then the rest is the same. So this is my Hamiltonian. But instead of putting the bracket that I just said, the 2 bracket is the double contraction on the n plus 1 form. Now, Chris has already shown that with this way of definition of the brackets, then this complex becomes an L-infinity algebra. The good thing is that it's antisymmetric. The bad thing is that it doesn't satisfy Jacobi. But the thing is that in the paper of Baez, Hoffman, and Rogers, they already encountered these 2 examples at the case of when n equals, but basically when the form is of dimension of degree 3, and these 2 structures, the one that I call Ham, and the structures that Chris defined for any n plus 1 form, they show that at the level of a 3 form, that they are equivalent. Now, one, as Dimitri calls it, the one that I wrote here, well, this one is not antisymmetric, but satisfies Jacobi. The other one is antisymmetric, but satisfies Jacobi up to homotopy. But somehow, Dimitri had already studied this kind of structures algebraically, and they have shown already that in the case of n equals 3, the 2 algebras are equivalent or isomorphic in some sense. So one is not antisymmetric, the other one doesn't satisfy Jacobi, but somehow all the information is there in both of them. So in this description, I expect that the same happens for n bigger than 2. What is useful from the description that I have here is that that's the one that will appear when I'll try to put an action of a Lie algebra, and I'll get nice information. So let me continue. So what is the idea again? So I forget that I have current algebroids, and I want to put an action on this object. And then I just think about principal bundles or vector bundles. So I have a nice map on the base, and I want to somehow extend it to the total space. So, well, what I can expect is that if I pull back one from the other, that these 2 are gauge equivalent. So this is the equation that I wrote in the middle. I want that the information given by one and the information given by the other be gauge equivalent. But in this setup, being gauge equivalent is just the same as being related by the derivative of an n form. And this is what Ezra was talking about. Somehow I want to do this continuously. So I'm deforming this form continuously, but there is an error on the deformation. I don't want to be to be the same, the pullback of the form to itself. So, and I keep track of how I deform it. In the case of what I was talking, well, there is a Poisson structure here. I just so far have nothing. I just have an n form, nothing else. So this is kind of a simplified version. But then, of course, these gauge transformation, which are these n forms, these b sub g, well, they may not behave nicely, as they may not be a nice homomorphism of groups. So then these forms in here, well, they have some error, and I just measure the error, and this is kind of a representation up to homotopy. So, but how do I keep track of all this information? This is the first thing that I would like to get. If I want to lift the action of my group in the manifold, just by pedestrian way, I would like all this information to be satisfied. And this information is a cohomology class in the differential cohomology of the group with values in the representation, which is differentiable forms. Well, I didn't write what exactly it was, but it's just the equations that I had before. Just continue going until they stop. So basically, I know the group act, the differential forms are representation, but there is a complex of representations, and I just simply say that I want some action up to homotopy. So the first thing that I would like to do if I want to bring an action of the group into the differential forms is that I have to lift this form, n form. I would like to lift it. So I live here in the n plus 1 cohomology, and I want to lift it to the n plus 1 differentiable cohomology of the group with values in the differential forms. Just a notation. This number that I put here is the total degree. And I put a bullet there because this is internal degree. So we have to add the degree of here with the degree of the group to get the total degree. So that's why I just put it there as a complex. So the first thing that I want to do is to lift this. We could lift it as just the closed form to another closed form, or as I know that I can just shift my current algebra to another one via the derivation of some, but I could just lift the cohomology class, either one. Then how do I interpret this at the level of Lie algebra? So I just basically take what I call the Van S map, so I just basically differentiate the identity, all these maps, and I get an element in the n plus 1 cohomology group of the Lie algebra with values in this complex. But how do I understand this information? Well, we should simply understand it as an L infinity map from the algebra itself to the symmetries of the n form. So let's recall that I have here my vector fields, and in the symmetries of the n form, I have all this information, and I could just project on the first coordinate, and I have the rest. So what I like is I have here a nice Lie algebra map. Well, I have to lift this and one by one so that I get a map, an L infinity map. This information is just given by what is that I want to measure for the students. I want to measure whether the map that I put here is a Lie algebra map. The defect of not being a Lie algebra map is measured by an element in here, and so on and so on and so on. Okay, so, but when I do this, it is clear that I'm just taking into account the fact that this is a G representation. I'm not taking into account that G is I'm not taking into account how the vector fields of some sense, how the vector fields of the Lie group act on these differential forms. So I have to bring that in. How do I bring that in? Well, I should have done it from the beginning, but I'm telling you how to do it pedestrianly. So I just basically, as I'm working the world of DG manifolds, I go and take the Lie group in this category, and I just take the Lie algebra of the tangent shifted one of the Lie group. What is this Lie algebra? Well, this Lie algebra is, just write it down. So I take the derivations of the degree less than 0 of my functions of the tangent 1. Then this is what it is. This is vector fields on the group, shifted 1, vector fields of the group. And this is contractions, this is just Lie derivatives, and I just take the invariant part, and this is going to be my left invariant. And this is my Lie algebra of T1G. But somehow what I'm bringing here is somehow this action of these contractions. So I furthermore need that the Lie algebra of this DG manifold act in the appropriate way in the symmetry. So I just need to do the natural thing. I need to lift the action that I have on the derivations on the differential forms, which is what is on the right-hand side, because the Lie group acts on M, so I have a map here from this Lie algebra to the derivations less than 0 of my differential forms. And then I need to lift this Lie algebra map to a map of L infinity algebras to the symmetries. Well, these ones are more difficult to write it by equations. But it's easier to see that any lift would give me a closed element in the n+1 cohomology of that differential graded Lie algebra with coefficients in the differential forms. So, well, in this case, very complicated way of writing it, when I take the functions on the differential graded Lie algebra, is just the Weil algebra, so it's contractible. So the whole cohomology is just the cohomology of M. But I still need the information that is the infinitesimal information. So I'm going to write down here, so how does this equivalent cohomology can be defined, because I will need it to show in the next slide. So this I learned from Camilo. I didn't know this, but he told me that this is very known, but I didn't know. So a nice way to get what is this, the differential on the functions, say the symmetric algebra, thanks to the zero algebra, thanks to the differential forms. Well, it's simply first define the differential on the functions of your algebra or of your DGLA. But in this case, somehow we already know, because this is the symmetric algebra tensor. So this is just the differential on the Weil algebra. So I'm going to put it in coordinates. So this is the dual of the bracket. And plus the curvature form. And the differential of this can be obtained from this one. So this is the differential, or the sum of these two is the differential in this part of the algebra. And then to get the differential on the differential forms is just simply the dual, in some sense, of the action. So what is this? So if I want to, now I go from the differential forms to the symmetric, and I need to do a shift so that everything maps to the right place. And I get the differential form. How does this one act? It acts by contractions. So I put the contractions on the appropriate directions of the vector field. How this one acts? This one's by Lie derivatives. So I just put it. And how this one acts? Well, it's just the differential. So when I do have the differential of this element and the differential in here, as it's a differential graded algebra, I can just get what is the differential of the whole cohomology. So I just want to point out that I have 6 terms that I will in a second match with a similar thing. So the question is how to make this into a global action. Well, now I have the infinitesimal version in one side. I have some sort of global version in some other kind of ad hoc. And I want to put something in the corner that would make the global action to map to this one that is not taking into account the action of this symmetric algebra. And in the other part, I have the action of the symmetric algebra, but I have the infinitesimal action of the group. Well, this, fortunately, was done by Ezra in 1995, I think. 3, 4?
3.
On Bot 70th birthday, Ezra published a nice paper. I was in high school. Which is a very nice differentiable version of equivalent cohomology for non-compact Lie group actions on manifolds. So, which is basically kind of it's a nice generalization of some result that had done Bot and to any action. So what is the idea? I'm just writing the same letters that Ezra wrote in his original paper, and this cohomology groups is isomorphic to the equivalent cohomology with real coefficients. But so, what is this cohomology group? So, well, a lot of formulas, but I will tell you each one of them what it is, and then you'll see how these things are appearing beautifully from each one. Well, there are 4 differentials. The first 3 are somehow natural to guess. The first is the differential of a differential form. The second one is basically coming from the Cartan differential. It's just the contraction along the vector field. So the first two differentials, I'm going to write them here. In this coordinate version that I put here is simply D plus contraction along vector field. This is the first two. The third one, what we see there is that we are taking into account that we have a G representation, and not only the group act on the differential forms, the group also act on the Lie algebra. That's what is on the right hand side. So to cross differentials, well, this differential 1 is this differential 1, this differential 2 is this differential 2. The third differential D bar has two pieces, as I just said. The Lie group is acting on the differential forms, the Lie group is acting on the Lie algebra, and those are these Lie derivatives. So this is the D bar, and this is the D bar. Where is it? Yeah, these two, of course. This is the action. So D bar and D bar, this D. And there is one missing. What is the one missing? The one missing is precisely that Camilo calls it, how do you call it, ascension map, or that you allow to basically, is the map that the identity map in the DGLA. So this is the one that tells us that the Weil algebra is contractible, this equality map. Well, that map, that thing is exactly the one associated to this operator. So this is just a simple and perhaps bad proof to show that the infinitesimal version of that is this one. So then we have something to fit in the diagram, which is this equivariant cohomology made by Ezra. And then, well, I say that to have an action of a non-compact Lie group on a closed form is the same as to have such a closed term. This is as close as I get. But yeah, of course, it's kind of a doc because I'm constructing it by hand, and I'm not telling you what is the automorphism group or anything. I'm just going to tell you what it should be the answer. But so I call it proposition. It could be like notice that. But so if I want to lift the Lie group action to the n form, to the closed n plus 1 form, well, I better find a lift of this thing. If I do, then I can make an action up to homotopy into the n form. And so, but this is nice because then we know that this is just equivariant cohomology, and therefore if I want to understand equivariant Rn bundles over T1m, they are classified by the m plus 1 equivariant cohomology group, which is no surprise because we knew it from before, that they're just KZn bundles. I just have 2 more slides, so I'm going to let you free early. But now, if we'll take a look, of course, at this whole complication, if we just take a look at the case when the Lie group is compact, then we know that this derived functor that was there that was taking variant is exact. So the cohomology is just given by the Cartan model. Just basically differential forms, tensor the symmetric algebra, take it invariant, and just use this differential here. Well, if I do that, of course, if I want to somehow lift my 3 form or my n form, I better lift it to an invariant one. This I can do because the group is compact, and because I can integrate and connect it, then I can integrate, and if not, then I can't. But if I can, then somehow all this information that I had to construct to make the lift simplifies quite a bit, especially in the case of the Lie algebra part, because of course we now have our Lie algebra here that we want to lift from vector fields. And here in the symmetries, that is vector fields plus 2 forms, plus n forms, sorry. We don't need the n forms anymore because we have the n form is, n plus 1 form is invariant. So we don't care about this part. So let me just put it in the appropriate way. So I want to do, so I have my vector fields, n forms, I have my Lie algebra here, it goes to here, and then I have to do the G1, and then this goes to the vector field plus n minus 1 forms, and this goes here, this goes here. So this part, I can just take my element and send it to the vector field, and I don't need the n form because the form is invariant. And therefore, this lift here, as you can see, well, it will give me, for every element, it will give me a vector field, A, and some n minus 1 form But this n minus 1 form has to map to here, so it's Hamiltonian. So what I'm just saying is that just because of this, if I have a compact Lie group, I can cook up right away a map from my Lie algebra to the Hamiltonian symmetries of my form if the group is compact. And this map turns to be a Lie algebra, a Leibniz algebra map. Because this element, basically, that is lying here, this element that is this thing together with the curvature forms has to be invariant. And being invariant, plus that I have this map, make this a Leibniz algebra map. So it's basically what I get here somehow the DG engineering that Marco, Gil, and Enrique did in their paper when they wanted to do the reduction. They said what should be the appropriate momentum map, and somehow from this description the momentum comes alone, but it comes automatically isotropic. It's already there. If I wanted to make it not isotropic, then I just have to not take an invariant element, and I just make it live in the whole complex of Ezra, and then it may live there if it's not isotropic. But if I wanted to be invariant the form, then it forces me already to be isotropic, because there was some comment that said they may not be isotropic, and I never understood why, but more or less now I understand. And of course, then one can just simply say that if I want to make an action into my current algebra, it just simply lift the G action to an equivariant form in the model of Ezra, Kitzler, and that would give you an action. Now, this is a lot of differential forms in several degrees, and they have a explicit meaning, but there are several. But this is somehow as close as I got. So, as I said, the problem is that somehow the answer is, it shouts the answer from the beginning, but somehow one has to go and get the answer. But this is kind of a pedestrian way of doing it. There must be some kind of sophisticated way to do it, but I don't know how to do it. As I prepare these things on the computer, then of course I went faster than usual, but we're all tired, so thank you very much.